So this recording is for the robotics class final project Braille reader. So the purpose of the project was to use filters to basically, whenever I would hold up a letter to the camera, it would tell us what the letter is on the screen. Unfortunately, I did face issues and I was not able to get that working. Currently, the project as is, it works right now as a playground where you can try out different thresholds with the binary and maximum minimum, and as well as canny edge, and they do a pretty good job at recognizing it once you get the right tune in. So this is recognized as D with the top three with a single circle and the bottom three with a double circle, and using a Fatsu threshold, it also is able to accurately find the dots and as well as the written letter at the bottom. For this portion of the project, I had the OpenCV file for JavaScript. So even simple template matching, I would get this exception catching is disabled and it cannot be caught. No matter what I did, I couldn't overcome that issue and it completely breaks the program. So I implemented a machine learning portion. So I got this Braille dataset from Kaggle, and basically they're 1,560 images with 28 by 28 size, black and white scale, and they have shifted with height. They're rotated and they're dimmed. So just a quick overview of what the dataset actually looks like. These are a couple of them, and I verified a couple of them to make sure that they were accurate. The actual model that we have is we're doing 2 layers of convolutional layers with a kernel of 3 by 3, and to avoid rapidly overfitting, we used a dropout every so often. So we have 2 layers, 75% dropout, followed by max pooling, another convolutional layer with 50% dropout, another max pooling, another convolutional layer with 25% dropout. We flatten that to get a vector where we start making predictions in the dense function. So for our activation function, first we're using sparse categorical cross entropy because of how we set up the output for the labels. We use a label encoder, so if we had used one hot encoding, we would need to do categorical cross entropy, and we use a sparse categorical accuracy. Now, for our model, whenever we would fit it, I did 10 generations whenever I would run it, because I would have very short epochs that would gradually increase the more training data I gave it. So every time we fit the model with the number of epochs, we would increase both the amount of training data it received as well as the number of epochs. So it's incremented by 20 epochs every fit, and incrementing by 5% more data per generation. And we do this for 10 generations. What I did was then I split the data 80% for training data and 20% for test data. So this 20% is just holdout data that I want to test out on the final product. The first model we built was a rectified linear unit with stochastic gradient descent as the optimizer with ReLU as the activation. So going through the generations, you see this bottom chart is the accuracy versus epochs versus the loss on top. And so as we go through the generation, you can see that we're going to end up overfitting eventually, and you can see the divergence that's there when we do overfit. There are instances where sometimes you'll get the data just behaving differently because we have such a high dropout that we may drop out the most optimal value, and that's okay because at the end it'll train itself and the data will end up not overfitting as well. After running that for 10 generations, we evaluated on the holdout data, which is about 89%, and the overall data is about a 95% accuracy. For the next model, I thought, hey, let's include the entire data set instead of just 80%. So running that model, we can see that we get 95% for our initial holdout data and about 98% for the entire data set. I also ran a ReLU Atom model, and running that, we can see where I also did the same thing where I held 80% and I gave it 80% to train first. And that first instance, we got an 87.5 for the holdout data and a 95%, close to a 96% on the overall data set. Once I reintroduced all the data for it to train on again, at the end we got a 97, close to a 98% for the overall data, and almost a 99% for the, that's gone. Almost a 99% for the overall data set. I gotta run this again, but it was on camera, and I'm glad I got it there because it can be a bit tedious can run this over and over again. But yeah, that's my project. If I had more time, I wish I could have married these things together and basically give you one cohesive project where I built the model to basically predict the value. But if I could change anything, I would probably just stick with Python instead of trying to do this in JavaScript with OpenCV.js. But it is what it is, and I'm proud of the machine learning aspect of it and the structure I built for getting ready to display the data back to the user. So thank you so much. Have a good one.